pleasure to introduce this morning's speaker to you, Dr. David Hu, who is an assistant professor in the Department of Mechanical Engineering, and he also has an appointment in biology. Dr. Hu received his undergraduate degree from MIT and also his Ph.D. in mathematics from MIT. He was then a postdoctoral fellow at the Current Institute in New York, where he also taught mathematics. And he was an NSF fellow for both his graduate work and his postdoctoral work. His research focus is on the properties of hydrodynamics and elasticity and their bearing on biological processes, with a special interest in the dynamics arising from the interactions of flexible textured surfaces. To this end, he's looked at locomotion and optimal propulsion on flexible or compliant surfaces such as water. And he's looked at the motion of locomotion of snake slithering, water striders, meniscus climbers, and also ants. If you haven't looked at his website, I would suggest you do so. There's some really cool videos and pictures on there. Makes you a little creepy crawly if you're like me and a little squeamish, but it's pretty cool. He also works on the water repellent properties of ants and other insects and how they themselves have fluid-like properties. And he's published in top-tier journals such as Nature and PNAS, and his work has also been highlighted in the Washington Post, the New York Times, National Geographic, NPR, to name a few things. So today he's going to be talking to us about ant rafts and other water repellent systems, and discussing experiments that elucidate the water repellent adaptations that a range of animals from insects to mammals make. So please join me in welcoming Dr. Hu.
Thank you very much, Priya. It's great to be here at 8:30 a.m. I thank you all for coming. We're going to talk about insects today, in particular how to stay dry to stay alive. I'm going to talk about a couple of my favorite model organisms for looking at water repellency. For example, this is a raft built by ants. We'll talk about that. We'll talk a little bit about how flying insects repel water. And if there's time at the end, we'll get to my wife's ex-boyfriend's Valentine's gift to her, which was this poodle, which was on Good Morning America last year. So I collaborated in particular with Craig Tovey. This is an image of the academic ladder you have to climb in order to get in my lab. It's arduous to reach the top, but the view is very nice. My collaborator Craig Tovey, he and I did this ant raft model I'll discuss. Nate and Andrew aren't here, I don't think. They did most of the experimental work. And I hired a number of undergraduates, some in particular to take the photos that you'll see throughout this talk and the videos, most of which are our labs. People usually ask me who funds this stuff. NSF Physics of Living Systems and NSF Biology, in particular physiological and structural systems. So you can check out my abstracts on NSF Online if you want to see more about my funding. Let's begin with the fundamentals. What you're seeing here is the mating dance or combat of the water strider. It's on the water surface. So this animal is basically somersaulting, jumping, wrestling. There's a headlock on the right-hand side here. And it's doing all this on the water surface. All this without falling through, which is just amazing. It's impossible at our scale, but on their length scale, it's not very difficult. So what's supporting the weight of these insects is surface tension, which is a force per unit length, or equivalently an energy per unit area. As a result, water surfaces tend to resist deformation. They act like trampolines, which prevent them from objects from sinking through if they're very small. I realize a lot of people probably research is not exactly organismal biomechanics, so I'm going to talk a little about surface tension for your own benefit. So when a drop of water is placed on a solid, there's basically two regimes that can occur. One of which is biologically favorable, such as this. We call this hydrophobic, and the other one hydrophilic. The idea is that if you're hydrophilic, water tends to form a very thin, flat layer and completely coat the surface. That's associated with an angle of contact of 0 degrees if it completely touches the surface. What organisms want is they want to avoid contact with the water, so they generally try to have these contact angles to be as close to 180 degrees as possible. 180 degrees would correspond to a perfect sphere. Now, if any of you are wearing water repellent pants, the way it works is through a combination of chemistry and texture. Chemistry acts to make the surface hydrophobic, near 180 as possible. And texture basically acts to make the water see a composite surface, basically a combination of air and pant material. So in particular, there are two laws that describe how that works. One is called the Cassie law, and it says there's this contact angle of the drop on a macroscopic scale, and it's a weighted average of the contact angle on the air and on the solid. And if, for example, which a lot of these surfaces are, I'll show you, if it's mostly air, the contact angle becomes very high. If a drop of water hits the surface with sufficient speed, it can generate a Wenzel surface, where instead of being supported on an array of air pillars, it actually penetrates and wets the surface. So this is the kind of thing to be avoided. Now, one of the reasons water repellency continues to be studied for the last 100 years is because of hysteresis, which is, if you're an experimentalist, is a terrible word, because it means if you measure something once, it may not be the same if you measure it again. In particular, contact angles have a range of values in nature. And this is due to on the microscopic scale, there's tiny mountains and valleys that trap the contact line. It's not raining today, but last week when it was raining, you might have noticed water drops will stick to your windows. And from the theory I showed previously, that shouldn't be possible because the contact angle should be the same on the top and bottom of the drop. But because of hysteresis, there's a minimum angle and a maximum angle, theta receding and theta advancing. And as a result, the drop looks kind of like my wife's pregnant right now. So my pregnant wife's belly, we're going to give birth in a month, and her belly's even larger than this. But as a result, you can see there's a vertical force associated with these different angles here. And that's what supports drops on windowsills. If any of your experiments involve small bits of water, you should continue to read. There's this great book by 3 Frenchmen, very little mathematics, that talks about capillary phenomenon. Now, so in my field, capillarity, the Holy Grail was basically 10 years ago when they discovered something called the sacred lotus. This is associated with Buddhism, but basically it's a particular plant. Bart, Lott, and Nienhuis have published this 10 years ago. It has 2,000 this paper has 2,000 citations. And the plant basically forms a Cassie-Baxter layer, so that most of this plant is actually covered in air and is due to very small pillars on the plant. As a result, when drops form, they form perfect spheres, and moreover, when they roll off, they carry detritus and things with them. So anytime it rains, the plant gets cleaner. So since then, you can imagine there's a ton of material scientists trying to publish on this, but there's still a lot of work that has to be done. In particular, waterproof fabrics, there's still a lot not understood why they're so fragile and expensive to make. There's still going to be it's still going to be a long time before we see this throughout our daily lives. So today I'm going to talk about 3 mechanisms that I think might play a role in making water repellency more robust. So let's start with what you're most familiar with. As Priya said, you might feel a little creepy and crawly, so you might want to finish the sandwich part of your meal. But we'll start with ants, in particular fire ants. So these are fire ants from the wetlands of Brazil, a place where it floods twice daily. This is composed entirely of ants on the water surface. Nothing else, no glue. This is ants holding on to themselves. Okay. So these ants have learned to adhere together, and over generations they've learned to do this in a very organized way. This is the topic of my student's Ph.D. thesis, and I only talk about the rafts today, but they're capable of building bridges in case they want to cross long obstacles. And they're also capable of building bivouacs in which to store their colonies overnight. These bivouacs, they can even open and close the holes in them to reduce a water loss and maintain temperature. Now, if you want to build something, you need a glue. And the ants' glue is basically their own claws and mandibles. But they basically can link together strongly enough that they can form these long chains in the lab. Here, let's go to this one first. Moreover, the ants are very strong. This is one ant holding up 20 of its neighbors. As I said, these are SEM images of the mandibles and the claws gripping each other. And these ants are very strong, and because there's so many, they act like a continuum, sort of like between a solid and a fluid. You can estimate an elastic modulus based on the strength of an ant, its size L, and basically the length of deformation of its arms. And this is basically, it'll be something similar to silly putty. Using the micro CT that was actually available in this building, you can visualize what inside the ant structure looks like. In particular, it's actually like the lotus leaf. It's a structure of mostly air. It's only 20% ant, 80% air. And what makes it so strong is that each ant has 6 legs and a large number of neighbors. These red points show you where it's connected to the neighboring ants. And you can see the neighbors connect all across the body. So we've seen that they can aggregate, but why? Well, let's see. So this is a typical experiment we'll do in our lab. This is a drop of water, and here's an ant. And you see, it has very poor properties if it were to try to swim. In particular, its contact angle is mild, so it sticks to water. It has adhesion. And as a result, if you were to try to swim and if you're an ant, you basically stick to water with every step. It's a terrible thing. Moreover, there's a high hysteresis. Basically, if you want to remove your arm from the water, you basically have to deform the contact angle a great deal. All of these are terrible for swimming. But luckily, these ants live in colonies, and they learn to cooperate. So what they've learned to do is build textured surfaces by linking together at the exact spacing that's required to prevent water from penetrating. One time I was going to ask the Georgia Tech swim team to see if they could build a raft like this, but of course they wouldn't be water repellent. But because they're on the length scale, on a very small length scale, water will tend not to penetrate these pores made between the ants. And by the Cassie-Baxter law I stated earlier, if they have half the area fraction air and half of it ant, their contact angle will become much greater than it was if it were solely ant. But you don't have to believe me. You can ask the ants yourselves. So this is what happens when you try to drown these ants. On YouTube, everyone wants to drown the ants, so everyone's disappointed when we can't drown them. I believe this has 1 million hits on YouTube. It's quite a large number of middle schoolers interested in our research. But you see, when you try to push them down, they basically form bubbles between them. This is all air pockets, and that prevents water from penetrating the raft. It's very non-intuitive. And if you push the raft even further in depth, you'll see they form this air layer. That allows them to stay dry even when underwater. This air layer has a limit, of course, because as you go deeper and deeper, there's going to be increasing hydrostatic pressure that will eventually push out these bubbles. What maintains the air layer, this is a common principle in nature. This is in the water repellent literature, it's always known that there's a hierarchy of length scales that prevents water from penetrating. In particular for the rafts, there's the spacing between the ants. There's the spacing between the legs. And on the legs themselves, there's these tiny hairs. For water to try to wet this very complex surface, it's got to do a lot of work. In particular, you can predict how deep you can put each of these structures underwater before water will penetrate those holes of varying size. Basically, to fill the pores between the body, you have to go 1 centimeter, but to fill the holes between the hairs, you have to go almost 1 meter. So this makes the ant very robust. This is a picture taken of an ant underwater that's floating gently upwards. And you see it's actually not touching the water. If you look very closely, there's a thin layer of air that surrounds its body. Biologists call this a plastron, or an artificial gill. Basically, the inward diffusion of oxygen is equal to the ant's metabolic rate. And this means it can survive indefinitely underwater simply by breathing the air absorbed into the air layer. Some engineers a couple years ago tried to build a version that's fit for humans on a large scale, but it's still having problems. So we've seen these ants have great properties when they're together. But how useful is this during flash floods? They have to be able to build a raft quickly enough for everyone to survive. For example, let's say we had a fire drill and we all had to go out on the water surface and build a raft, everyone in this building. How quickly would that happen? Well, everyone has to carry their belongings. We have our laptops and our centrifuges, our pipettes and things like that, your lab notebooks. And we're basically trampling upon each other to try to get away from the water. Basically, we have those that are being trampled upon, and those are the tramplers. How do we do this in an organized way? So I'm going to show you a video of an experiment where we take an ant ball. You do that by taking ants and swirling them up like this in a cup, and that turns them into a perfect sphere. And then we put them on the water surface and watch what happens. So this is a time-lapse video of about about 200 seconds. And you see the ants know intuitively to transform from a sphere to a pancake. They build. This is about 8,000 ants, so this is probably the entire, this is 4 times the mechanical engineering class. But 8,000 ants, they build, link together at the edge, and eventually they form a structure that has an equilibrium. It looks a lot like a drop of spreading fluid. Here's a smaller number of ants, so you can see a little bit what's happening at the edge. They're all running toward the edge frantically, and then getting to this equilibrium structure. And then, of course, you have those students that are the black sheep that are just doing their own thing. Everyone thinks they can start their own colony. There they are. And here's a side view, where, again, you see it goes from a sphere to a pancake shape. There's some interesting stuff going on here, I think enough for a whole other PhD thesis. These ants can actually walk underwater on wet surfaces. It's partly because they actually extrude a drop of hydrophilic and hydrophobic fluid, a composite drop that allows them to stick to almost anything, even if it's wet. So you see there are 2 layers. There's basically, like I said, there's the underclassmen. Those are basically on the bottom that are wet. And then there's upperclassmen that are on top that are dry. How does this happen? So I'm going to talk a little about modeling. I know we're in IBB, so this is not the math department. So I'll try to talk about it in an intuitive way. But the idea is basically to predict how quickly this ant droplet spreads over time. And we basically parameterize that by the area of this raft. So we can simply record that from a video. And from the area, basically from every square centimeter, we know the density of ants. We know it's 30 ants per, basically in the area of my pinky nail. So we're trying to predict the number of ants on the bottom layer of the raft as a function of time. It starts out as the number involved in the sphere, and it extends all the way to what I'll show is about half the colony. The model inputs, we basically have the total number of ants. This is basically the weight of the ant ball. Each ant's 1 milligram, so 1 gram of ants is 1,000 ants. The time scale of the problem is set by the walking speed of the ants. Basically, the ants walk, they basically run like hell to get out of there. And if they run twice as fast, the raft is built twice as quickly. And each ant basically walks a pinky width in a second. There's a number of layers of the raft in equilibrium. So that's something we can't predict. I think that's based on how strong the raft needs to be to survive waves and things like that. In experiments from 1,000 to 10,000 ants, that's always consistent. It's 2.5 ants. So the ants have a local rule that they basically says, we want to build a raft that's 2 ants high. So here's the model in a nutshell. Imagine you're in a horde of people. What you want to do is get out of there as quickly as you can. Well, if you're starting at a random position within the horde, you basically want to run as quickly as you can to the edge of the horde. And that's what they do. They basically take a beeline for the edge in a random direction. Once they get to one edge, they try to find an escape. Of course, there is none, so they turn around and basically run to another edge. And from one edge, they keep on running to another edge and another edge until they basically get trapped. So every time they get to an edge, there's actually some small chance that their friend reaches out and grabs them. If their friend grabs them, they become part of the raft, and that's how the raft expands. So we can actually measure the probability that they could grab with a probability p. And if this is a unit raft, that means it's a 1 centimeter in diameter. We can predict by integrating over all possible angles the green and the pink. And so that gives us an expected travel distance on a raft of unit width. And that's actually the entire model, because now you know what one ant, how long it has to travel to get to the edge, and how long before the raft expands. The rest of the model is assuming the following things. Well, every ant basically does something that's similar. We can't predict what one ant does, but over 10,000 ants, these averages are very, very good. So the number of ants that basically add to the side is proportional to the number of ants running around on top, divided by the travel time it takes to get here. Now, the number of ants running on top, we call that little n of t. The travel time is basically this number dimensionalized by the radius and divided by the ant speed. We can convert radius to the number of ants using this density number I mentioned, the number of ants in a pinky area. And so that number of ants is collecting at the side of the raft every unit time, and they're forming a layer h thick. So this gives us a differential equation for the raft growth. It relies on the random walks of the ants. And there's basically two regimes you have to take into consideration. One, in the very beginning, where the top layer is saturated with ants, and that's happening in the beginning. So here you have the top is filled with ants. They're all going in random directions. But because the raft starts out small, the number of ants on the top is small, and so the growth is slow. That's why it's very slow in the beginning. But as the raft expands, you get a larger number of constructors, and so you see this raft starts increasing in speed. The rate increases. But as this thing gets bigger, eventually you're going to run out of ants, and that's what happens at the very end, because you basically have a diminishing number of ants on top, and as a result, the speed slows down, and you have this very nonlinear behavior. Note this is a log-log scale, so it's very nonlinear. In comparison, if you took a drop of shampoo and put it on the water surface, it would spread out according to a power law, so that this would be straight. But here, it's nonlinear. So that's the model of how quickly the ants can do it. Oops. And this all happens within 200 seconds. So they're very, very good at it. And as a result, in the videos I showed you, you can have 10,000 ants and 0 will drown. You'll have literally 0 casualties. Now, these rafts aren't always circular. For example, this is an example of what happens when the raft reaches land. It actually docks. So this is very analogous to a cell. I would call it like an amoeba, which reaches out a flagellum. Essentially, these ants have local information. They see the wall here, and as a result, they walk towards it. And this thing extends and extends and extends until it gets to the edge. This work is still ongoing, but I think it will have repercussions in the swarm literature. There's still a lot of fundamental questions about how quickly you can build things. In particular, there's now new devices. I don't know if you've seen this. This is a cubular modular robot that can basically construct larger robots by connecting together. The grand challenge of robotics in 2009 is basically take a bucket of robot parts, dump it out, and have this bucket of parts build bigger robots. So we're hoping to collaborate with roboticists to do that. And as you who do biology know, swarming together, for example, in this amoeba-like dictyostelium to form a spore, a slug, and a stalk, all that is due to this kind of swarm behavior. Okay. So that's the first story I wanted to tell. It's about cooperation. Now, the next story I want to tell is about insects that work alone. So I want to talk a little bit about how insects fly in the rain. So this is a housefly, and this is a water drop that hits the housefly. If you're trying to design an insecticide, this is probably the very worst thing that can happen, because it means all your insecticide gets on the ground and none of it gets on the fly. And part of the reason is because these, like the ant rafts, these flying insects are actually highly hydrophobic. As a result, people had to very carefully choose droplet sizes that will actually touch the insects. This is a scanning electron microscope picture of aerosol insecticides, which are only 20 micrometers, so 1/5 of your human hair, that actually stick to the insects by inertial impaction. But anything larger will basically bounce off. So I want to talk about how mosquitoes fly in the rain. So mosquitoes are a funny animal. They like humid environments, but no one's really asked how they can fly in these conditions that are wet, like rain and fog. So to get you situated, let's think about the two competitors. We've got a raindrop here and a mosquito. They're basically roughly the same size, a couple millimeters. But the mosquito is mostly, its body is very thin, so as a result, its mass is, the mass of the raindrop is 2 to 50 times a mosquito. So it's basically the equivalent of us being trapped underneath a bus. They're very, very heavy. Moreover, their speed is very high compared to the mosquito. Mosquito probably travels at most 1 meter per second, this far in a second. But these drops at terminal velocity, if you ever try to see them on high-speed video, they're quite fast, 5 to 9 meters per second. The drops, because of their high speed, they carry a great deal of momentum that's basically thrown laterally anytime it hits a solid surface. So this is a drop hitting a bird's wing. And the momentum, so basically the momentum of the drop, the mass times its velocity, and the time scale of the impact, which is about a millisecond, that gives you an idea of the forces that are involved upon this impact. And it's basically 10,000 mosquito weights, so an extraordinary amount of force. So how do these mosquitoes survive? So first of all, these drops hit the mosquitoes actually quite frequently in a rainstorm. You can calculate this based on the mosquito's impact, the area of potential impact, that of its wings and its legs, which is about 30 millimeters squared. And a very heavy rain, it'll rain about 50 millimeters an hour. That's basically a height. If you fill a bucket 50 millimeters an hour, that's basically the rain intensity. Combining these two, we can get the frequency of impact upon the area of the mosquito. And that's basically, you get an impact 1 every 25 seconds. So it'll be quite frequent if they're in the rainstorm. Moreover, there's basically 2 regions of impact that are important. The direct impacts, which are in the red area, and the glancing impacts, which you can see as the majority of the area, the purple and the green. And so that's, if you look at the areas involved, the glancing impacts are about 3 times more likely. And that corresponds to our experiments. So this is, we basically make simulated drops, and this is a mosquito able to recover easily after perturbation by the drop. Let's show it again here. Now, the drops I'm going to show you in the following experiments are all slower than terminal velocity, about 2 meters per second. And you can calculate the force applied on the wing that is causing the torque on the insect. And it's only about 2 mosquito weights. So this is easily survivable. Like I said, the next kind of impact that can occur is when it hits the body directly. And partly, if the insect flies basically with a vertical body position, the drops will simply glance off the back, even though it hit directly. You can see the hydrophobicity is very important here in preventing the drop from deforming greatly. And I'll talk more about this deformation in a second. But if the insect's unlucky enough to basically be flying horizontally, if it gets impacted directly, they'll basically form a lump mass with a drop. So this is a direct hit with a drop. You can see when they get hit, both of them go together. In mechanics, this is called inelastic impact, where you have two objects that stick together upon impact. I'll talk about how we can predict the momentum precisely after impact based on their relative masses. In all these cases, these insects can free themselves. In this case, we don't exactly know why. We think it has something to do with the high drag on the legs and wings that allows it to separate. So to make progress on this problem, it's actually very hard to do the experiments with insects. So we choose mimics, basically small styrofoam balls that have the same mass as the insects. And we think the mass is actually the most important property in determining the impact phenomenon. So like I said, if you have two bodies that impact each other, the momentum before impact is going to be equal to the momentum after impact. So as a result, the ratio of the speed after impact to the speed before impact is going to be the ratio of the masses involved, in particular the mass of the drop to the combined mass of the drop and mosquito. Now, mosquitoes are so lightweight that the drops lose almost no momentum upon the impact, maybe only 2 to 7%, 17%. On contrast, if you take a dragonfly, it'll lose about 90%, because that's actually several times a drop weight. And because they lose very little momentum, as I'll show you, the force is very low. So this is very non-intuitive. It's very different from the impact on a bird's wing, where the drop is spread. Here, the force and the momentum afterward depends strictly on the weight of the mosquito compared to that of the drop. There's some cases here where the theory here doesn't fit very well, and that's the case if the drop hits the side of the mosquito mimic and spins it. There you have some dissipation, and as a result, you get lower final speed. So these are two mimics of the same size compared to drops of very different size. Particularly, here's what would be drizzle, and here's what would be typical rain. And as you see, what you would expect on a solid surface is that if a drop hits it, it should deform greatly if it's large. But in this case, the force is determined by the mass of the mimic. So the small drops happen to deform more. Although the small drops deform more, it's the large drops that actually have the largest number of G's. So the number of G's involved here is around 100. Now I'll get into that in a second. Here, let's. Okay. So to predict how many G's there are, first I have to prove that the drops don't splash. And I'm not going to go into this in great detail. But basically, what keeps the drop together is the surface tension. And anytime the drop deforms, it generates increased Laplace pressure inside the drop. This is the Navier-Stokes equation, basically. The momentum of the impact, which is the change in the drop speed over the time of impact. The Laplace pressure due to the increase in surface tension. And gravity, which is negligible in this case. The deformation time, basically the amount of time for the drop to deform, can be estimated by the change in speed over how much the drop deforms in radius. And the pressure gradient can be estimated by the change in pressure due to changing from a sphere to an ellipse. Using these together, we can basically predict how much this drop will change in radius as a function of the masses of the two items. And it fits almost precisely our data. Stating that basically we can predict how much the drop deforms depending on the size of the insect. In particular, the small drops will deform more, as shown up in the left. So we see that drops deform rather than splashing. That means you can assume they're inelastic impact, that they go together. And this is the number of G's that is measured from these experiments that I showed. So it's actually quite high, the number of G's. Let's calibrate this for you. the human tolerance was taken on a rocket sled. This guy basically took this rocket sled at a high speed and then stopped it suddenly. He suffered about 20 Gs, which is known to be the human limit, and they call that eyeballs out, because his eyeballs detached from his retinas, so he kind of had trouble seeing for the rest of his life. So that's about 20 Gs, how much you can withstand. And when I get to this dog work, I'll show these hairy mammals actually shake much higher than that, and so they have to close their eyes to prevent their eyeballs from popping out. But I'll get to that in a second. But so depending on the size of the drop, you can basically get between 50 and 300 Gs on a single mosquito. It may seem like a lot, but you have to keep in mind these mosquitoes have a very strong exoskeleton. And 300 Gs, when you're a very lightweight mosquito, is only about 0.6 grams of force. So that's essentially like the weight of a feather that's falling on the mosquito. So it's actually very low. We've done basically impaction experiments where you basically squeeze a mosquito on a analytical balance, and they can survive basically an order of magnitude higher than that. So they basically have no problem surviving, depending even on many large range of drop sizes. Let's see. So I think I'm gonna. Okay. So this is a video of a mosquito being hit by a jet. There's still a lot of things we don't know. For example, if it's by a series of drops, how the mosquito will behave. Here, the number of Gs is only 100. So even though it's being hit by a jet that's going 10 meters per second, the number of Gs is still quite survivable. I think I'm going to skip some of this stuff. Sorry. Okay. Okay. Oops. Okay. So we've seen two methods of water repellency. One based on construction of the animals with each other. The other, the animal acted like a Lagrangian particle. It was so small that basically the drop just carried itself with it, and as a result, the drop didn't splash, and the animal survived. Now, you wouldn't think surface tension is useful on the larger scale, but it turns out drops, for example, if they're leaving an animal, have to depart from small bundles of hair. So surface tension, as I'll show, is important in determining how quickly animals have to remove water. And as Laura knows, I got Iacuk approval to do this, right, Laura? Okay. So in the last 10 minutes, let's talk about how animals shake to remove water. So it's actually harder than you would think. If you shut the door of your office and go on all fours, as I do on occasion, you try to do this, it's actually quite difficult. And the reason is, well, you have to have 4 legs. The front legs basically turn clockwise, the back legs turn counterclockwise, and you've got to do a self-ringing motion so that your body rings itself out and spins at high frequency. The result is quite spectacular. As I'll show, they do it at various speeds. The number of gravities involved, which we can calculate, is basically between 10 and 70. So for these animals, it's a lot larger than the human tolerance. And if you shake your head very quickly from left to right, it does hurt. Moreover, it's actually quite effective. So I like to compare these things to washing machines, even though they're very different processes. But your washing machine, as you know, will dry your socks within about 10 minutes. But this gets the animal 70% dry in about 1 second. You can measure the weight of the animal before and after to determine how dry it is. And for rats, they basically got almost all the water off instantaneously. So it's very, very good. So I'm going to talk about how it happens and how it changes depending on animal size. First of all, why is it even there in the first place? It seems like it's just a cute little phenomenon. But in actuality, it's a matter of life and death for these animals. There's this great article, 1928, by J.B.S. Haldane. He was a geneticist, called On Being the Right Size. It's a great article for your classes. It talks about the consequences of scaling. But the article says, so if you come out of the bathtub and you step on a scale, you'll find that you have weight a pound heavier due to the water on you. The water is basically forming a very thin layer, a 50th of an inch thick, and that altogether weighs about a pound, which is nothing. But as you get smaller and smaller, this weight increases. So a wet mouse, it turns out, has to carry about its own weight of water when it comes out of a bath, and a fly has to carry many times its own weight. You can see the problems of losing this water become increasingly difficult as you get smaller and smaller. This is coupled to the problem that water takes a lot of energy to evaporate, especially in cold weather. For example, 1 pound of water takes around 250 calories to evaporate from the body. That means an average-sized dog, which weighs about 60 pounds, with a pound of water in its fur, one can calculate that it takes about 20% of its daily calories just to dry that water off. So this is a very big deal in cold climates. This is a typical experiment in our lab. We take a pink straw and we do fur particle tracking. So this is a pink straw that's gently taped to the back of the dog. And you can see that's actually the back of the dog. So the back of the dog is going 90 degrees to the left and 90 degrees to the right. The dog's skin is very, very loose. Those of you who've taken freshman physics, you might remember this as simple harmonic motion with an amplitude of around 90 degrees. If you take the dog's skin and move it yourself, you'll see it's as I said, it's very loose. And it can move about 60 degrees on its own, which means the backbone of the dog is only moving 30 degrees, a paltry amount. So the very back of the dog, the vertebrae is moving a very small angle. This means that if animals had tight skin, the velocities would be one-third as high if they had loose skin. And as I'll show later, the centripetal forces will be only 1/10 as high. So it's critical that these animals have loose skin in order to get the high speeds associated with this large amplitude. You can verify that the amplitude of the backbone is small in these high-speed X-ray videos done at Young-Hee Chang's lab. You can see the backbone doesn't move very much as they shake. Okay. Now, one of the most interesting about biology is that diversity is the spice of life. So these animals they've got to basically go from a very small size, the size of a mouse, all the way to a grizzly bear, and still figure out how to get the shaking mechanism to work at all these different sizes. It's like trying to design a washing machine that works in your pocket and works as big as your car. Let's see how they do that. This is the smallest shaker in the world. It's a mouse, and it shakes quite fast, 30 times per second. So in a single second, it'll shake 30 times. And you can see it's effective at removing water. We get a little larger. This is a rat. This is shakes about 20 times per second. So it's slower than the mouse, but still capable of removing water. You notice the mice and the rat, they tend to lift their front paws up off the surface. The other animals keep their forepaws on the ground. We don't know why that is. The other thing you'll notice is they keep their eyes closed. We call this shaky bacon. This animal, it's a pig. It shakes at 10 hertz, so 10 times per second. So this is becoming in the realm of what is reasonable. You see, it's also pretty good at getting rid of some of these hay particles and things like that. We were surprised at how good the sheep was. Sheep have lanolin in their fur, which makes it pretty water repellent. But you see, it's actually quite good at shaking. Surprisingly good. So that's at only 6 times per second. So we're getting slower and slower, and the animals are getting more ferocious. So we went to the zoo. This is another animal from the zoo. We, and by we I mean my grad student and a hose. We filmed this animal. This is a bear. It's about 4 times per second. Of course, the most ferocious animal of all humans, so you can try this at home. You can only shake your head at most 2 to 3 times per second. Is that my? No, she didn't want to be associated with our experiments. So there's this trend, this clear and obvious trend that the small animals shake faster. Why is that? Now my answer is that all these animals, if you're a drop in an animal, you don't know if you're on a grizzly bear or you're a mouse. So the drops have the same physics associated with them. And in particular, on the animals, hair tends to form bubbles. For these animals to lose this water equally easily, they basically have to have the same centripetal force to fight the surface tension of the drop. Because the animals get a smaller radius with decreasing size, they have to compensate by increasing their frequency to increase the centripetal force. So let's see if this hypothesis matches the experiment. So the first is this is a fact found by McMahon, how basically the mass of animals changes with their cross-sectional radius. Basically, lighter animals have a smaller radius, as you expect. The second is found by Tate. He was a pharmacist, actually. He actually invented IV dripping. But basically, he found that if you have, well, he didn't actually use a tuft of hair, but he used a tube of varying radius. If you have the radius of the tube, you can predict precisely how heavy this drop is going to be when it ejects. And the force balance that dictates the size of this drop is the centripetal force, which depends on the velocity squared, or the frequency and amplitude of the shake, and the radius, of course, and the surface tension, which is basically the circumference of the drop, 2 pi times the radius of the drop. Here we use the radius of the hair clump because that's where it's contacting the solid. There's an extra function here due to the fact that some of the drop is left behind as it ejects. But this relation between centripetal force and surface tension shows you how frequency of the animal should scale with radius of the body. And we substitute radius for mass because it's easier to measure. So this prediction states as the animal mass goes up, the frequency should go down due to the negative exponent. This is how this prediction matches with the experiments. We studied about 35 animals, 16 species, and 8 dog breeds. And they all fall along this pretty nice fit. It's pretty good. You see this is 5 orders of magnitude in mass. It's rare you can have such a large x-axis. The y-axis goes between, it was 3 to about 30 times per second. The best fit to this line has an exponent of 0.22, where the theory is 0.19. So it's quite close, considering that we didn't take anything of the animal into account. We only took the physics of the drop. Some of you might wonder, well, maybe this is just due to as larger animals, they tend to go slower just because of their size. But scalings from the literature, for example, on the trot-gallop transition, basically how quickly they can move their legs, when they transition from a trot to a gallop, they have a very different exponent, 0.14 compared to 0.22. So it's not simply due to the fact that they're larger. We believe they're actually tuned to these drop sizes. So we believe this finding in the future will be useful for autonomous robots. There's some nice examples of autonomous robots, for example, this Mars rover, that are basically lose their capabilities because of exposure to dust. In this case, the power was lost on these sensitive solar panels due to collection of dust, and it only regained power once a wind swept through and blew the dust free. So for a robot to be truly autonomous, it really has to learn to remove particles from itself. Another insight this study provides is that this mechanism is really terrible for fluids of different properties. I call this an ancient mechanism ill-suited for modern times. Basically, these furry mammals, they evolved loose skin to aid with locomotion. Shivering eventually turned into shaking with a combination of fur. The only ways to get rid of water are either to have dense, oily hair, like these otters do, or to have this inertial shaking at very high frequencies, where centripetal forces beat surface tension. But you can check pretty easily that this doesn't work if the fluid has a very long time scale. For example, crude oil drips very slowly. And as a result, any animal that's coated in a high viscosity fluid will not be able to do this. And that's a large reason why these oil spills are such a problem. So I'm going to try to wrap up. I've talked about 3 very different topics, but they all dealt with surface tension. We saw that basically synthetic fabrics and plants, they basically have a combination of chemistry and bumpiness that acts to repel water. And animals, because they're able to move and have all these different properties from plants, they've learned to repel water in very different ways. The ants, they can build surfaces by linking together. These mosquitoes, their mass dictates the impact phenomenon. And these mammals, they do what we call active water repellency, where this is a new idea in the literature. You use energy to remove drops. And in terms of waiting for evaporation, it's actually very effective. So I want to leave you with this thought of active water repellency, which is involving construction or use of energy, compared to passive water repellency, involving structure. A lot of the reason I was able to do this work is because of my joint position in biology, in which I basically teach a new class every 2 years based on insects. So I taught a class 2 years ago on ants, which is called Ant Lab. This year, we're teaching a class on insect flight. There'll be a poster session based on their work in about 2 weeks, if you're interested in learning more. And another thought I'd like to leave you with is that I think these images and these problems are a great way to teach physics to young audiences. This is one of the articles that was written on our work. You can see these cute little ants. I think kids really like this stuff. So with that, I'm happy to open the floor for any questions. Todd.
Did you notice any capacity for locomotion of the entire raft?
That's a good question. I get asked that sometimes. That the ants are so good at cooperating. Can they actually like row themselves all together? It seems that it hasn't happened yet. In part because they have to build the rafts very quickly, within 200 seconds. You imagine you have this flash flood. They've got to build it almost instantaneously. As a result, each of the ants is randomly oriented. So each of them is facing a different direction. Some of them are maybe even sideways. And so their legs are all pointed in different directions. So they can't seem to... I think if they're pointed all in the same direction, maybe they might be able to row together. But because they're all pointed in opposite directions, they don't seem to be able to coordinate. It is the ant raft, I mean, if you play with it in the lab, it's surprisingly it has very low drag. So you just blow it, this thing will just... simply just glide very easily, and it's because it's mostly air. So it is quite possible if they could just basically coordinate themselves, but they just aren't, I don't think are oriented properly. Yeah.
With these ant rafts, you said like they self-assemble. So you take that raft off this and that on dry land, and they disassociate back to the ants.
It takes them longer to disassociate, but they do have to do that, especially when they get to land. When they basically get to land, they only have a couple seconds to realize land is there, and then they have to grab on to land. So they do have to sense land is there. But it's not as quick. Partly, so one basic thing about the swarm systems is that they only have local information. So only the ants touching land will know that they have to get there. Whereas in the raft, they're all just trying to get the hell out of there as quickly as they can. So they're all running in random directions. So they don't really need to have this directionality associated with it. So it is slower, but they do disassociate. Mm. Yeah.
Great talk.
Oh, thanks.
I assume that you model most of your things with pure water. What happens when you introduce, say, salt water or something is not? Do things change?
This is one thing that's always struck me. In the lab, these experiments are actually quite difficult to do because small traces of surfactants, for example, if your clothes, you go like this with your clothes, there's small bits of detergent, any small residues will cause these rafts to sink immediately and everyone to drown. Basically, the plastron layer is dissipated if you have lower surface tension, and they basically can't breathe underwater any longer. So in the lab, it's almost impossible to do unless one's very, very careful. But in the wild, there's a whole bunch of biofilms and other things on the surface that I would also think that would lower the surface tension. These animals spend a great deal of time cleaning themselves in the wild. They'll clean themselves basically half the time. So I think partly it's to deal with those kinds of things. But it's a really good question. I think it's a question of chemistry, but I think it is pertinent, but we don't really know the answer to that one.
So would they float on salt water?
Salt water is only 3% lower surface tension than fresh water, which is the high surface tension of water combined with anything else. So they can float in salt water. Often they'll float for weeks, because they're in the pantanals of Brazil. So sometimes they'll get swept out to the ocean. So sometimes they'll have to float for weeks before hitting land, and they'll actually start eating each other. And things like that's been documented. Yeah, in the back.
Once they form the raft, is there turnover with the raft, or the ants on the bottom end up on the top and circulate, or are they relatively stable?
So when I describe the raft, I always think that it's worse to be on the bottom, because that's where it's wet and cold. And there is turnover. For example, we tried to take a picture once of what the raft bottom looks like. This is kind of a Zen thing. And what we did was pick off the ants on the top. But what it turns out is that the ants at the bottom will only stay there if there are ants on the top. So as you pick the ones on top, the whole thing shrinks. And which states the ants and this has been documented before, that they have little sensors. For example, they'll stay in these configurations only if they feel feet on top of them. As soon as you don't get enough feet on top of them, they'll release their neighbors. But it also requires a lot of coordination that we don't understand. For example, if you're on the bottom, you got 5 or 6 neighbors, and the links are one way. Someone grabs you, or you grab somebody. But somehow, if they want to escape, they can. They can sort of tell their friends, "I want to escape," and then they let go. So it's not clear how they do that, but they do exchange. They do exchange if there's less ants on top, and sometimes they'll just exchange randomly. If there's no one walking on them, you'll see a hole in the raft, and eventually it'll get filled. Yeah.
Do you think this is going to have an activity the layers?
Mm-hmm.
Do you think that's really important, or why is it like 2, 4, 5 layers
The question is what sets the equilibrium height of the raft? I think like I said, I think partly there's some strength issues. If it becomes a single layer, it's actually not very strong. And they have this rule that they have to be underneath other ants, otherwise they'll just escape. But I think there's also evolutionary pressures and things like that. If there were a third layer, there'd basically be an extra safe layer, because there are basically birds picking the ants off from the top and fish eating the ants from the bottom. So I think if there were a third layer, everyone would want to be sandwiched in the middle. But if there's basically people on the top there being eaten, people on the bottom being eaten, then it's sort of more fair. So I think somehow that's what ended up. I think there's probably important reason why there's not more than 2 layers. We documented they build these towers and things, like the bivouacs. There's many layers in the bivouacs. So they're capable of building very many layers, but they just don't for the rafts. I think it's due to because of these pressures and things like that. Yeah.
What will happen if you put 2 rafts in the water and they somehow join together?
I just reviewed a paper on this last week. These fire ants, they're very territorial. So one colony will basically is very seldomly aligned with another. If you have 2 rafts from different colonies, it'll be like pirate ships. They basically link together, form this mound, and then kill each other, and everyone will die. There's no survivors. So you don't want 2 rafts touching each other.
So you'll have to divide one raft into 2 and then combine again?
If you do that, then I think it's okay, as long as they're from the same. They can sense almost instantaneously if there's someone from the same or different colony. Yeah, in the back.
You said that the mice and rats close their eyes when eating.
Mm-hmm.
Do you think that's anything to do with, I guess there were genes that's converted on their eyes and the way it's feeding them with it?
I think I I think that would be tough to study, first of all. But I do think your eyes are somewhat protected if you close them. But maybe they also get dizzy if they keep their eyes open and look at the world going that quickly. But they all tend to do that. So it's quite a large number of G's. I mean, if you can imagine moving 30 times per second, that's quite fast. So there's not really much precedent for animals dealing with that many G's. Maybe if there were, we could see if they also close their eyes. Yeah.
I would imagine that like the least thing on the head versus the back would be different. So do parts of the body drive that?
Yes, that's true. Our model basically just considered basically the top of the back. That's the only place we can measure the amplitude. And as I said, we measured how wet the rats are after the shaking, and they basically have 30% of the water remaining. I think a lot of that is on places that they're basically not able to move, like their hindquarters and things like that. They generally they stay somewhat wet, but those are sort of away from the core regions of their body, so maybe that's less pertinent to them. I mean, sometimes you'll see dogs, they'll sort of whip their tail afterward to get rid of the water in the tail, but they definitely don't stand on their front legs and shake with their back as well. So they basically, I think they've done as best as they can, but you're right, there's some parts that probably remain sopping wet. The thing about capillarity is if you have parts on the dog that are wet, it'll sort of seep, sort of equilibrate, sort of seep and make the whole dog mediumly wet. So I think if they wait a little while, eventually they'll be able to shake again, and that water will be able to come off. Well, thanks for all your questions. I hope you enjoyed the talk.